Okay, we have an interesting integral here today. We've got the integral of x to the a minus 1 over 1 plus x dx. And I've been kind of obsessed with this one ever since. This came up in a previous video as part of another problem. I think it was one of the UK problems where after like a u substitution we got to this. I do want to define this a value a little more carefully here on the exponent, because we're going to be getting a general form for this in terms of a, and we want a to be a real number, and we want a to be greater than 0. And to get started with it, what I want to do is just notice the similarity. If we have a 1 here, this is kind of like our formula for the geometric series. So normally we have, this is our standard formula for the geometric series. We would have for 1 over 1 minus x. For power series, we can write this as n equals 0 to infinity of just x to the n, where we want x to be, the absolute value of x to be greater than 1. Sorry, we want the absolute value of x to be less than 1. And that reminds me, I forgot the bounds on this. Sorry, this is going to be going from 0 to 1. That way we know all of our x values are between 0 and 1, so this condition's fine. But what we have in our problem, it's not exactly 1 over 1 minus x, it's going to be 1 over 1 plus x, which I can write, sorry, I don't really want to write it like that. Let's write it like this. Let's write this as minus x, so we can just input a minus x into this formula. If we do that, we can write it like this. But then that's actually, let's split out the minus sign, and I can write it like minus 1 to the n times x to the n. So now we'll just take this and plug this back into our integral here. But then from here, we've got the same base here, x and x. So I think it's going to be nice to just combine these together, multiply this in. When we do that, get rid of this. This is going to become adding exponents n plus a minus 1. And then from here, all I want to do is let's just swap the order. Let's swap the series with the integral here. The reason is the integral is going to be easy to do. This is just going to be power rule. Everything in the exponent's a constant. We're justified in doing this because we have absolute convergence over here, because we started with the geometric series. So let's do the flip here. And then from here, we'll just go ahead and integrate this thing. The minus 1 over n, this can actually come out front here. Then integrating this with power rule, we're going to end up with x to the n plus a over n plus a. And we just need to evaluate this from 0 to 1. Here you can see kind of why we wanted to do this with a minus 1, not just a. You could have done it that way, but the reason is it's just a little cleaner, because then this minus 1 here goes away. Then evaluating this, when you plug in 0, it's nothing. When you plug in 1 here, this part is just going to be 1 over n plus a. And now at this point, this is where things get a little bit tricky. What I want to do in this is I want to break out the even terms from the odd terms. And when I say even terms, I mean even n. So how we can do that is just plugging in, for our even terms, we'll plug in 2n. That way all those will be even. And for the odd terms, we'll plug in 2n plus 1. So let's see how this is going to work. We're going to have the sum from n equals 0 to infinity. Then we'll combine these together here. So this will become plugging in 2n for our even term here. Our exponent becomes 2n. I could do a different variable, but it's not going to matter. So I'm just kind of plugging it in like a substitution here. And then here, we'll plug in a 2n here. So we'll have 2n plus a. And then for our second one, same kind of thing. We change our n to 2n plus 1. And we'll have 2n plus 1 here to get the odd terms. This will become 2n plus 1 plus a. Now, a couple concerns you might have here is you will notice what we have right here. This is not absolutely convergent. The quick check, without getting too far into it, for absolute convergence, you put absolute values around it, and then what's going to happen is this, the minus 1 goes away, right? The absolute value takes care of the sign. So basically, this is going to be like 1 over n plus a. But this series, assuming we still have, this is still a series, this is really similar to the series of 1 over n. As long as a is finite, this isn't going to really change anything. So our series of 1 over n, the problem with this is our harmonic series. This actually diverges. And so what this means is any rearrangement of the series is not allowed right now, because it could change the value of the whole series. It could change the value of our answer. It could mess everything up. The first thing is, doing this though is not actually a rearrangement. A rearrangement is, we're saying we're actually changing the order of the summation. We're changing the order of terms. At this point, we haven't done that because this is exactly the same as this. If you start plugging in n values, you're going to get the sum of the exact same terms in the exact same order as this. So here we haven't violated anything yet. The trouble is I'm about to manipulate this and I am going to change the order. So we are going to have rearrangement. We're going to violate this. I think for my justification, I'm going to put that in a separate video because it's kind of long-winded. It's probably going to bog down this video if I give you the whole explanation right now. But my claim basically is that within one of these groups, within one term here, I'm going to say you actually can have rearrangement within a single term. I think technically you have to like redefine the partial sums. So sort of like we get rid of this sum, we get rid of this original series here and we don't consider that. We say this is our new series. And then all that we're doing, all of my manipulations are going to be just rearrangements within a single term of this new series. So that's my short answer why I think this is justified. I'm going to have to do another video because I think it is pretty technical and some parts of it I don't actually even know. And so yes, you don't have to take my word for it, but I am going to say in this video, the rearrangements I'm going to do are actually fine and don't create a problem with this over here. Okay, so let me get rid of all this stuff over here because this isn't going to matter at this point. Now first, dealing with these exponents, this again is always even. -1 to an even power is always going to be 1. Over here, this is always odd. -1 to an odd power. This is always going to be -1. Let's do it like this. Let's create this as a 1 and create a minus sign in the middle here. Then next what I'm going to do is let's factor a 1/2 out of this just because we've got a 2 on the ends in both places. So when we do that, what's going to happen on this first one, we end up with 1 over n plus a over 2 here. And then on the second one, we're going to end up with, this is going to become n plus a plus 1 over 2. And then here what I want to do is I want to add in a 0, but in a special way so we can set this up. To add, I'm adding 0 here. I'm going to add in these two terms, 1 over n plus 1, 1 over n minus n plus 1. And then kind of group all this stuff together. We're going to have the positive one with this one, and then the negative one with this one. What I'm trying to do is set up the Digamma function on this. So let me rewrite this with the 1 over n plus 1 terms and see what we have. Okay, now from here I split this up into two sums like we have here, trying to match it to our form here for the Digamma function, where we have this series expansion for the Digamma function minus the Euler-Mascheroni constant here, which is something like 0.577, plus a series similar to what we have here. So like this one is perfectly set up because see the input in the Digamma function is going to be this z. So on this one, we have our z right here. On this one, I need to change the order. Notice the 1 over n plus 1 should come first. I can multiply in a minus sign. Then we'll have a minus sign here. And then let's just bring a minus sign out front on this one. So then for this one, our input, our z value is just going to be a over 2 for this one. So in order to get this exactly the way we want to use it, let's add the Euler-Mascheroni constant on both sides. So it cancels out here. And now we've got an expression for the sum that we have over here. So using the formula, let's go out of order because we've got the minus sign between them. So like we'll start with this one. For this one, this is going to become the formula Digamma of our z, which is going to be a plus 1 over 2 plus Euler-Mascheroni constant. And sorry, we've got a 1/2 on the front here. And then for the second one, we've got a minus 1/2 in front. Same kind of thing. Here's our z, here's our z, so we have Digamma of a over 2, again, plus Euler-Mascheroni constant. But because we have a minus sign between, the constants are going to cancel. We can put these together. Let's factor out the 1/2 and like put it all over 2. So what we're left with is just going to be Digamma a plus 1 over 2 minus Digamma a over 2. And that's going to be it. And this might seem like kind of an unsatisfying solution, but on the other hand, we do have, this unknown a in here. So if we look at some different values of a, we'll see that we can get some pretty good answers in this. One good value, I think, one interesting value to look at, it's interesting when a equals 1. When a equals 1, we have x to the 0 or 1, so the whole integral becomes this very simple integral 1 over 1 plus x. If you do this one out, this is just going to be natural log of 2. So then plugging into our formula with a equals 1, we should be able to get back to ln 2. So let's see what happens. Digamma 1 plus 1 over 2 is just going to be 1. So here we have Digamma of 1 minus Digamma of 1/2 all over 2. It's useful to memorize a few common values for the Digamma function. I have a playlist where I calculate some of these values, particularly I know I did both these, so we'll just use those values. For Digamma of 1, we got minus Euler-Mascheroni constant. for digamma of 1/2, we have minus 2 ln 2 minus Euler-Mascheroni constant. Now this is all over 2. What's going to happen when you multiply the minus sign? The constants cancel. Minus times minus is plus here. 2 cancels with 2. And we get back what we have there, ln 2. But another good one, I think this is where I thought of this. I had a video not too long ago where I actually did the same problem, but we had a equals 4. So in that one, if a is 4, using this, then our integral, this becomes x cubed. And my solution in that other video was just, let's write it down here. So the solution for that one was 5/6 minus ln 2. Let's see if we can produce that by plugging in. So plugging in a 4 for this first part, this becomes 5/2. And then for the second part, plug in a 4, we have digamma of 2 all over 2. So for this, I want to use the recursion formula to reduce the input. So if we have digamma of z plus 1, we can reduce this to digamma of z plus 1/z. So using it first on 5/2, reducing it by 1, we get digamma of 3/2 plus the reciprocal, which is going to be 2/3. Then use it again. We want a value for digamma of 3/2. We can reduce this to digamma of 1/2, but that's the value we just saw a second ago. So I'm just going to plug that right in. Minus 2 ln 2 minus the constant plus the reciprocal of 1/2. That's going to be a plus 2 right there. So we'll plug that back in for 3/2, and we have our value for the digamma of 5/2 now, which is going to be minus 2 ln 2 minus Euler-Mascheroni constant plus 2 plus 2/3. That's going to be 6/3 plus 2/3. We have 8/3. And now we need a value for digamma of 2 over 2. Calculating digamma of 2 is going to be pretty easy, or you could remember it, but we'll just use the formula again. So for digamma of 2, we reduce it by 1, we get digamma of 1. Reciprocal of 1 is just 1. This value we know is minus the constant, then we have plus 1. So let me just take that and plug this in here because I'm kind of running low on space. So when we do that, we're going to end up with plus, reversing the sign, plus the constant, minus 1 here. This is going to cancel with this. Then let's just simplify 8/3 minus 1. I can write minus 1 as 3/3. So what we have here is minus 2 ln 2 minus, subtracting these, we end up with actually plus 5/3 over 2. 2 is going to cancel here. This becomes 5/6, and we get back the same solution. 5/6 minus ln 2 matches that. Okay, there you go. Another interesting example with the digamma function. Thanks everyone for watching. Have a good day.